Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the last video we cleaned up the C++ code for lighting as well as fixed a few bugs. So now we are ready to optimize the light-culling shader, which is going to be the topic of the rest of this episode. So I updated Visual Studio the other day, and one of the features that got worse this time is editing shader files. They have added IntelliSense support for hlsl files, which does syntax highlighting and code completion and formatting. However, it does such a horrible job, especially with formatting, that I had to turn it off. Unfortunately, turning it off means that we now don't even have the rudimentary functionality that we had before, and it ends up looking like this. Which is perfect, if you feel nostalgic for how we wrote code in 1985. That's not the case for me though, and therefore I'm going to edit our shaders in Visual Studio 2019, which I haven't updated for a while now, just to have a backup for functionality that gets worse with each new update. Anyway, here I already opened the shaders that we are going to update in this episode, and as a warming up, I'd like to simplify the lighting functions here a bit more. We are using a simple Wang lighting function to calculate diffuse and specular lighting, and I'd like to remove that when we are rendering lights without attenuation. This is basically debug light visualization, and we don't need it to be that accurate. So we just use the light's color if it's not behind the surface that we are rendering. That's why I still use this dot product. Let's see how it looks. We have a warning here about comparing signed and unsigned integers. I don't know why I used a signed integer here, but it should be a U32. Okay, looks good. Let's start optimizing the light-culling shader code. Before I forget, let me fix this mistake in the code. We don't need to subtract 1 here, because we can have as many lights as max lights per group. Now I'm going to copy this entire shader code and optimize it. So we'll eventually have an optimized shader and the original one, and we can compare them both in quality and performance using conditional compilation. We see that after duplicating this code, we can still run the application. I'll start by rearranging the variable definitions. We'll get to the low-hanging fruits that give the most gain in performance in a minute, but moving these variables makes the shader also easier to read. Another benefit is that it makes it easier for the GPU to hide memory latency when the read from memory happens much earlier than where the value is used, like we see here for the depth variable. We can do another small improvement by not calling clip-to-view function. Here we are multiplying a vector with a matrix. As you can see here, there is a matrix vector multiplication and a division. However, we only need the z component of the result. Let's have a look at the projection matrix. When we use this matrix in our shader, it's going to be read as column major, which means that it's transposed. Also, in order to avoid having to memorize these expressions, we can give each non-zero element a name. I'll call them A, B, C, D, and -1. Let's have a look at the inverse of this matrix. This is a matrix we multiply with our vector in clip-to-view function. So, as in our shader code, the vector is 0, 0, the sample depth, and 1. Remember that the W component should be 1, because we are transforming a position vector. It would have been 0 if we were transforming a direction vector. Looking at the result, we see that we need to divide by W component in order to undo the perspective divide. As you can see, the only component that matters is the Z component, and dividing it by W component will give us this expression. Using this formula, we can calculate the depth in view space by directly using the sampled value from the depth buffer. Note that it's easier to get D and C values from the projection matrix instead of the inverse projection matrix. So I can just define C and D here, and instead of calling clip to view, we can calculate the depth directly. Let me first get the group frustum here as well. Now we can calculate the depth value in view space. Note that we need to negate this value to do these comparisons. That's why I left out the minus sign in this equation. And we can remove the old code. Note how much simpler this section has become. Okay, now we are going to optimize the most expensive part of the shader, which is the light culling section where we do the intersection testing. Here we have a branching in our code which could have a negative effect on performance. And the reason is that this code is executed by a bundle of threads at a time. We call this bundle of threads a warp for NVIDIA and a wavefront for AMD GPUs. In hlsl, they are simply called a wave. NVIDIA's GPUs have 32 threads per wave, whereas AMD's GPUs have 64 threads per wave. So a thread group with 256 threads is executed in 8 waves on NVIDIA GPUs or in 4 waves on AMD GPUs. I'll explain waves in a bit more details in a later video, but for now you can view a wave conceptually as something that executes each line of the shader code 32 or 64 times in parallel. Looking at it this way, it's easy to see that branching is detrimental for wave performance. Imagine some threads in a wave taking the first branch while others take the second branch. Since this code is run by all threads in a wave, this means that both branches are executed by every single thread. However, the results are discarded for each thread depending on what branch the thread actually needed to take. We can improve this by using a bounding sphere for the spotlights. As you can see here, we have bounding spheres for each point light, but we are using a cone for spotlights. As I explained in the previous episode, a cone is not a great bounding volume for spotlights anyway, so let's have a look at how we can construct a sphere that envelops a spotlight as tightly as possible. Here we have a spotlight with a range and a cone angle between 0 and 90 degrees in both directions. We can construct a bounding sphere using this equation, which is the light range divided by 2 times the cosine of the cone's half angle. However, as you can see, when this angle is larger than 45 degrees, the bounding sphere starts to blow up and goes to infinity for a 90-degree angle. We can solve this problem by using another equation when the cone angle is larger than 45 degrees. We can get this sphere by multiplying the spotlight's range by the sine of its cone half angle. Here we see that this isn't a good fit for smaller cones. However, when the cone angle passes 45 degrees, it becomes the best fitting sphere. So for the cone angles less than 45 degrees, we use this equation, and for larger cone angles, we'll use this one. In our shader, we can add a function that constructs this bounding sphere for each spotlight that we are testing. Here we can create a sphere that has the radius with this default value, which is for narrower cone angles. We also need to move the center of this sphere in the direction of the spotlight. If the cone angle is larger than 45 degrees, the value of the cosine of half penumbra will be less than this number. In this case, we use the second equation with the sine of cone angle, which we can get from the cosine value. This time we need to move the sphere's center with a value proportional to the cone angle's cosine. Now we can rewrite this part in order to use a sphere as bounding volume for both point lights and spotlights. So we create a sphere for point lights and we overwrite that sphere if the light is a spotlight. Then we can use a single intersection function for testing against the group frustum. Of course, we have to return the result when we calculate the bounding sphere for cones. And I forgot that we didn't include the cone angle cosine in the light-culling info. But that's okay, we can put that in the cone radius just to test our shader code. So in our C++ code, whenever we write to cone radius, we fill in the cone angle cosine instead. Now we can construct the bounding sphere using cone radius, which actually contains the cone angle cosine. It appears to be working, but let's have a look at the bounding volumes, which we can do by enabling the light-culling heatmap visualization. Well, the point lights look right, but once again the spotlight seems to have a bounding volume that's too big. So I must have made a mistake somewhere. And it's even the case for narrow light cones. Obviously not good. Let's fix it. First I'll check the value that's written to cone radius. This appears to be correct. Let's see what happens if we only use the equation for small cone angles. Well, this is really strange. Looking again to see if this value makes sense for wide cone angles, which it does. Oh. Obviously, if we want to overwrite this sphere, we shouldn't declare it twice. And also, we should not make it constant. I mean, if someone would watch this video without context, they would think I learned programming yesterday, wouldn't they? Ah, there you go. This looks more like it. And this square is smaller when the spotlight cone is narrower. Awesome. Let me add a compile time define and use it to toggle between the base implementation and the optimized one. Also, we can use it to define variables in light-culling info, depending on which implementation we are using. So if we are using bounding spheres, we need the cone angle cosine. Otherwise, we need the cone radius. And in the C++ code, we set the right field depending on whether this definition is set to 1 or not. I think IntelliSense died on me again, so I might need to restart Visual Studio soon. In light-culling shader, we can now use the cone angle cosine. Here we can also use this definition to toggle between the two implementations. So when we set this to 0, we can use the base implementation. But I need to fix my copy-paste errors first. Okay, so this one is the original shader, and you can see it's again clipping the spotlight edges. And this might also be the right time to ask ourselves if we gained anything by doing this optimization. Fortunately, we have everything in place in order to measure the average frame time. So I'll use a release build and turn off this sleep timer. Let me also use random lights. I'm going to write down the average frame times for 64,000 lights and 4,000 lights. Remember that we need to optimize for a common use case. Most games use between 0 and a few thousand callable lights. so we need to keep that in mind when optimizing. Okay, I really need to restart Visual Studio. And we should turn off the heat map. So the base implementation runs at about 16 FPS. I'd like to point the camera a bit more towards the center of the scene, so there are more lights in view of the camera. Okay, so it's more like 15 frames per second. Now let's measure with 4000 lights. That looks like 163 FPS. And then we measure using bounding spheres. With 4000 lights, it's about 172 FPS. And for 64,000 lights, it's 16 FPS. Although this isn't much faster, we can definitely see some improvement, so we know we are on the right track. We made the effect of having a branch in the shader smaller, but we didn't get rid of it entirely. We are still testing if a light is a spotlight, in which case we call this function to construct a bounding sphere for it. We can eliminate this branching by moving the bounding sphere construction over to the C++ side. However, the time's up for this video and we'll have to continue this in the next one. Hopefully you learned something new as well as enjoyed watching this video, and as always, thank you for joining me and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!